do that. There's all sorts of very complex OS-level UX controls which hook into a text box. If you implement your own text box using Canvas, all this stuff will be broken by default. For example, Control plus left/right for moving a word at a time. This is Alt plus left/right on a Mac, I think. There's another keyboard shortcut to go to the start/end of a line or the start/end of the input element. These shortcuts are OS specific and can be overridden in the user's OS level settings, which you don't have access to from JavaScript. There's a mountain of shortcuts like Control plus A, Control plus /C/V, etc. They all vary per OS. You have to implement them correctly on every operating system. International character input methods. How would you type Japanese/Korean/Chinese characters into your text element? Undo/redo support. Text selection via the mouse, the keyboard, and on mobile by touch dragging to select. Accessibility like voiceover and dictation. No matter how dedicated you are, I guarantee your custom Canvas element will never correctly implement all the features already available in a simple HTML text input element. I am aware of the trade-offs and generally I agree. That is what I meant by it can overcomplicate things. It is all trade-offs, and for some usages, it might be a valid one to remove the dependency on the DOM. I see it as an option for a heavy app in the browser. This is a fake similar to what Figma does or Flutter. Also, I am not referring specifically to text editors, although I could imagine something like Vim working with this approach in the browser without trying to replicate an HTML text input element. Google Docs does that and it works. Not perfect, but good enough. At any rate, I don't buy the argument that because Rust is fast and WebAssembly is comparably fast, then it makes sense to push your data structure, especially a text buffer, down into WebAssembly. To store a buffer in a plain text editor with no syntax highlighting, I'm not going to fight you on that. I'm glad pure JavaScript is fast enough for your needs. But doing collaborative text editing with a CRDT adds some extra requirements that your text editor's buffer might not have. For example, this is 1 millisecond even for very large documents. The same would not be true in JavaScript, and I might need to use bigger files. Merging concurrent changes. Like merging a long live branch. This currently involves getting fancy with a B tree. This is fast enough in Rust. It would be orders of magnitude slower in JavaScript. Undo support. When you hit undo, you need to ignore any more recent typing from other users and just undo the local user's last change. This is subtle. When edits happen, we need to convert between your line, JS column tuple and whatever the CRDT uses internally. Diamond types specifies edit positions by counting Unicode characters from the start of the document. So we need to convert between line call and Unicode offsets whenever local or remote changes happen to broadcast or apply the changes. Rust plus WASM let me make all of these operations essentially instant. I can do that because I can use an appropriate data structure and algorithm for each operation. And, sure, JavaScript's array is pretty fast, but if you ever need something more complex than array, your performance will suffer massively. Personally, I feel much better writing this code in Rust plus WASM. I'd integrate diamond types with your text editor by just passing edits back and forth across the module boundary. I agree that it probably doesn't make sense to share a text buffer between JavaScript and WASM. One URL. I'm glad pure JavaScript is fast enough for your needs. In this case, the bottleneck at 9 million lock is not CPU cycles but memory usage. That's where I am considering pushing down into WebAssembly, but whatever function inlining, optimization, V8 is doing, it is probably still faster than the overhead of JS minus WebAssembly function call. I have no doubt WebAssembly will edge out again. Merging concurrent changes, like merging a long live branch. This currently involves getting fancy with a B tree. This is fast enough in Rust. It would be orders of magnitude slower in JavaScript. I guess my point is, why do you need balanced trees? Is this a CRDT specific thing? Can you implement CRDT with just an array of lines/gap buffer? Undo support. When you hit undo, you need to ignore any more recent typing from other users and just undo the local user's last change. This is subtle. From my understanding, the whole point of cdarts or any command-based design is express changes to the state as the delta, in which case, you only have to stack/remember the set of commands and not have to store the state on every change. I'm not sure if this overlaps with the data structure choice other than implementation details. And, sure, JavaScript's array is pretty fast, but if you ever need something more complex than array, your performance will suffer massively. Personally, I feel much better writing this code in Rust plus WASM. I was just looking into typehead arrays. From my understanding, the JS runtime will use a hashmap or double linked list if the array elements are homogeneous. In the case where the JS runtimes know it is homogeneous, they will fall back to those typehead array/fixed length buffers that are continuous in memory. So on the JS side, arrays can be as fast as typehead arrays thanks to the compiler. Consequently, in some benchmarks, they will effectively be the same. The question is whether the speed of a native array is faster than the speed of a typehead array such that it pays for the WASM minus JS overhead, and I guess this depends on the application and the access patterns of that interop. In this case, the bottleneck at 9 million lock is not CPU cycles but memory usage. That's where I am considering pushing down into WebAssembly. How often does this come up in practice? I can't think of many files I've opened which were 9 million lines long, and you say lock lines of code. Are you doing syntax highlighting on 9 million lines of source code in JavaScript? That's impressive. I guess my point is, why do you need balanced trees? Is this a CRDT specific thing? Can you implement CRDT with just an array of lines/gap buffer? Of course. It's just going to be slower. I made a simple reference implementation of use automerge and sync 9's list types in JavaScript here. 1. This code is not optimized, and it takes 30 seconds to process an editing trace that diamond types in native Rust takes 0.01 seconds to process. We could speed that up. Use does the same thing in 1 second. but I don't think JavaScript will ever run as fast as optimized Rust code. The B tree in diamond types is used for merging. If you're merging two branches, we need to map insert locations from the incoming branch into positions in the target merged branch. As items are inserted, the mapping changes dynamically. The benchmark I've been using for this is how long it takes to replay and re-merge all the changes in the most edited file in the Node.js repository. That file has just shy of 1 meter single character insert/delete operations. If you're curious, the causal graph of changes looks like this too. Currently it takes 250 milliseconds to re-merge the entire causal graph. This is much slower than I'd like, but we can cache the merged positions in about 4 KB on disk, or something, so we only need to do it once. I also want to replace the B tree with a skip list. I think that'll make the code faster and smaller. A gap buffer in JavaScript might work ok. If you're keen, I'd love to see that benchmark. The code to port is here. 3. Undo support minus, in which case, you only have to stack/remember the set of commands and not have to store the state on every change. I'm not sure if this overlaps with the data structure choice other than implementation details. Yeah, I basically never store a snapshot of the state. Not on every change. Not really at all. Everything involves sending around patches. But you can't just roll back the changes when you undo. I type AAA at position 0 the start of the document. You type BBB at the start of the document. The document is now BB bar. I hit undo. What should happen? Surely, we delete the AAA now at position 3. Translating from position 0 to position 3 is essentially the same algorithm we need to run in order to merge. I was just looking into typed arrays. I tried optimizing a physics library a few years ago by putting everything in typed arrays, and it was weirdly slower than using raw JavaScript arrays. I have no idea why, but maybe that's fixed now. Typed arrays are useful, but they're no panacea. You could probably write a custom B tree on top of a typed array in JavaScript if you really want to, assuming your data also fits into typed arrays. But at that point you may as well just use WebAssembly. It'll be way faster and more ergonomic. 1 URL, 2 URL, 3 URL. What are your thoughts on the JavaScript CRDT implementation? I'm admittedly pretty new to the space, so I don't know much about performance comparisons. Haven't noticed any significant performance problems with it using it for collaborative editing on 100,000 word documents, but would love hearing what you think. It's fine. I think it's the best CRDT out there right now, but Kevin had a few years head start on me. I haven't done a lot with his personally, and I don't agree with a few of Kevin Johns' design decisions, but none of them are deal breakers. The way deleted data is encoded in use is awkward. Versions store a list of which content has been deleted, so versions are bigger than they need to be, and you can't replay the editing history without stored snapshots. I think the knowledge of which elements have been deleted should just be saved into the binary format alongside the inserts. For JavaScript objects, use pretends each value is actually a list with everything after the first element ignored, so it can reuse the logic for list editing. This is overcomplicated compared to shelf or something like it. Use's internal structure is a linked list with cached offsets. This works ok in practice, because inserts usually appear close to each other, but it means use has own -2 performance to process and edits rather than and log. Diamond types via WebAssembly is about 30x faster as a result, though, as you say, use is still plenty fast enough in practice for most applications. And this gap will narrow once yours is working well. Use can have an interleaving problem when concurrent items are prepended at the same location in a list. The current new diamond types file format stores the origin position plus parents information instead of storing left origin/right origin fields. This lets DT have a smaller file size while storing more information than you stores. And I think this format is easier for applications to encode and work with, and it will make pruning easier when we get to it. We should also be able to load and save faster than use, but I'm not benchmarking that yet. But all of this stuff is pretty minor. Use works well in practice, and it's quite mature. Performance will only get better with the yours Rust implementation. For diamond types, I had the benefit of being able to copy some fantastic implementation ideas from use. If diamond types is better than use, it's because I'm standing on its shoulders. I think Lemire's measurements are unacceptably lazy. WebAssembly is faster than JavaScript on the right things. There are many measurements showing this. Typically, measurements that show JS on par or beating WebAssembly either end up falling into micro-benchmarking traps. One small, hot loop, something gets dead code eliminated, or they end up relying on a particular type of dynamic optimization that WebAssembly engines don't yet do, inlining, escape analysis. With Simed and threads, WebAssembly can absolutely crush JS performance. URL. Why would WebAssembly engines need to do inlining and dead code elimination? My impression was that WebAssembly is basically native level code, save for register, allocation, and some Arch-specific PEFL optimizations. Dead code elimination is the job of the C++ compiler. Generally, I don't disagree, but not all producers are LLVM. And JS inlining is driven by dynamic heuristics, speculatively inlining likely candidates, whereas statically compiled C++ code, generally, doesn't have speculative inlining. So a WebAssembly call indirect will not get dynamically optimized into a guarded inline. Isn't Simed new in this release of the spec? How can WebAssembly crush JS using Simed if they only just added support? It's been implemented in browsers for longer than the spec has been out. In fact, one condition of a proposal being merged into the spec is that 2 production engines must have implemented it. I don't care if it's faster, the same, or even slightly slower. The sooner I can start working on large applications with a strongly typed language that isn't just transpiled to JS, the better. My point is that compilation targets are somewhat arbitrary. Non-JavaScript languages have been compiling to JavaScript for a long time. What difference does it make for you as a user of a language that it compiles to WebAssembly than to JavaScript or any other VM? JavaScript being garbage collected, having a rather complex runtime, not having proper integers etc., makes it a rather unfortunate compile target. Yes, you can do it and it is done, but JS idiosyncrasies leak into the source, langs pretty easily. That's a good argument but more of a maintainer argument than a user argument. From a user, it should be transparent except for performance and FFIS. Well, the user perspective is, suddenly, there are compilers for all kind of languages targeting the browser because WASM makes it easier for the maintainers to build them. Sure, you could have implemented unsigned integer semantics on top of bool arrays in JavaScript years ago, but if the result is too slow, you have gained because the compiled C++ code does not run fast enough to be usable. Regarding numbers, JavaScript supports bigints now, which makes the situation a little bit better, but maybe a lot more complex. I wish they were somehow better supported by JSON. Parse though. URL. Compile to JS is a leaky abstraction that gets messy when JavaScript's type system and built-ins collide with your languages. Some languages also need specialized tooling for their compile to JS stuff, rather than treating it as just another compile target. I usually find it causes more problems than it solves, but I'm hopeful that someday WebAssembly can make compile for web transparent enough that non-JS languages really feel like a great experience in the browser. You could use Dart, I guess. Flutter is similar to WASM apps like Figma in that they manipulate a canvas, not the DOM directly. I'd assume most WASM apps in the future will look more like that than true DOM manipulation. There are others, however, such as written in Rust, or Blazor in C number. Interestingly enough, Dart is also pretty deep into adding WASM as a compile target to act as an alternative to the current compile to Optimist.js approach they do currently in the browser. You are right though, they are going to be the first big WASM/Canvas and WebPoo framework as opposed to the generations of JS/DOM. It will be interesting to see where they land with it. I'm quietly hopeful, especially once you get sorted in the browser too. I think the real test is going to be when they decide to migrate over the multiple $1 billion of revenue project that Google adds is from JS-based Dart to WASM-based Dart. Work going on here, but not much to look at now, just source and no docs URL.